Hello, my name is Zoran Sjanic, and I'm going to talk about the poster called Particle Filtering Approach for Data Association. We start with problem formulation, where we trying to find the data association between the landmarks and the measurements of these, and encode it in a variable called C here, which is a correspondence variable. We can solve this problem by maximizing the fit function, and that is going to be done with a particle filter in this case. An example of how this correspondence variable looks like for a simple example can be seen here. Particle filter is an algorithm that is a sequential Monte Carlo algorithm that is trying to find the estimate of a certain variable or a state, where in this case is the correspondence variable. There are three important distributions: transition, proposal, and likelihood here that we will describe here. For the data association, we use the transition and proposal density, which are the same because of the certain version of the particle filter we are using. In this case, we are first trying to find the subset of all the landmarks that we are going to try to find association for, and then we use uniform or non-uniform proposal, where the PDFs are given here. An example of non-uniform proposal distribution is given here. The non-uniform utilizes the measurements much more than uniform proposal, which doesn't utilize them at all. The likelihood is given here, and the likelihood is consisting of two parts. One part that is trying to describe all the non-observed landmarks, and one part that is trying to describe all the observed landmarks. An example of likelihood is given here for the case of two landmarks. The results are quite promising because here we are comparing to the nearest neighbor, which is a deterministic approach, and we see that the non-uniform proposal will always beat it, no matter the number of particles, while the uniform proposal is approaching the performance given with the large number of particles. However, this is not for free because the relative execution time is much higher compared to the deterministic approach, which has a constant, no matter the number of particles, of course. So this is something to be looked into. For the conclusions, we evaluate the performance of this approach on a small 2D simulation example and compare it to the nearest neighbor. It has the best performance, but its computation cost is increased, and the more thorough performance investigation as well, application real data are the next steps. Thank you.